So this talk is basically called Oops, I Pwned Your Router. It's a talk about embedded security within router distributions, essentially. It's not any sort of 0 day per se, at least I'm not releasing anything here, but I did want to talk about, I worked with a particular embedded system, and I wanted to talk about the flaws that I found, and just from the perspective that, you know, this is, probably 15 years later that we're still finding stuff that was fixed, you know, back in the 1990s, late 1990s. So I'm David Bryan, consultant with TrustWave Spider Labs. I do all sorts of pen testing, have lots of fun with that. I'm the president of the hackerspace out in Minneapolis. We've got an 8,500 square foot space with all sorts of fun toys, metal shop, wood shop, etc., etc. I actually teach the welding classes out there as well. I have a lot of fun with that, and I'm going to be doing a metal camp at Tour Camp. So if you guys are coming to Tour Camp, maybe come and weld some stuff. I do electronics, hacking, all sorts of fun stuff. Yeah. All right, so embedded systems and security. So what's the deal? Why an embedded system? Why would you use an embedded system? Are we not awake? Cheap, right? Cheap, secure, well, not really secure, but cheap, right? And really the goal is it's a little device. It's a tiny device that does all the work of what you're needing to do, right? I've got up here a Router Station Pro. It's an open source embedded router. However, all the same principles apply to a lot of the devices that are out in the market. Has a very small memory footprint, usually only running in 16 to 64 megs of memory. This guy has 128 megs of memory, which is quite a bit. Usually the storage is limited to 4, 8, 16, 32 megs, somewhere in there. It's also running on, like we said, low-cost hardware. So low-cost hardware means, you know, the chips are maybe $30 for the device instead of, you know, $80 to a couple $100 depending on what you're buying. Little to no disk storage. So when I say that, what I'm talking about is that they don't have a file system that you write to actively. One, because a lot of the older memory file systems would crap out after so many thousand write cycles. You know, there's gates that you're flipping on and off. So instead of having lots and lots of space, they basically went for reduced cost, which means that, you know, those original file systems, those memory file systems or storage systems were very expensive. So, all right, well, instead of, you know, building a system with 128 gigs of space, we'll do 4, 8, 16 megs. And the developer tools, I don't know if anybody's seen this, but the developer tools typically don't include anything about security. Does anybody like that picture? Do you know what the picture is? It's someone starting a barbecue, actually, at our hackerspace. So the idea here is he doesn't care about what? Safety, right? He wants to get it going, get it lit up so that he can grill some meat. All right, so you remember the 1990s? Vaguely? For some of us, I remember the 1990s. You know, 1993, 94 is when Linux Slackware 0.99 kernel was released. And embedded hardware was kind of coming around, but not really. More so, what we're looking at is the software and the distribution, how the software was put together. It is been essentially lifted from that small code base and now put in these embedded devices. And I say that because a lot of them are based on BusyBox. So BusyBox is a great concept, but it doesn't really have the security built into it. There's no shadow file by default on a lot of the distributions that are out there, right? So that's why I say 1990s. This is like, in the 1990s, when you got a system, you know, you had to disable services, do system hardening. Does anybody remember, you know, inetd.com? I mean, you had to go in and actually turn all the things off because it sucked for security. Oh, and by default, there's one user. And that's the only user that you use, which is root, because why would you ever have more than one user? Right? What's the problem with running as root? You can do anything. That's right. It means there's no controls, no restrictions. All right, so JTAG. How many people here have heard of JTAG? A few. Excellent. JTAG is our friend. It's pretty cool. Allows in-circuit debugging. Allows you to read the flash firmware. Allows you to read the contents of the memory registers. You can halt a machine, reset a machine, and the tool that I'll be using, or that has been used in the past, is called OpenOCD, which is Open On-Chip Debugger. So you can essentially tell the CPU, hey, enter this debug mode, and then show me your memory. Show me the money. Anyway. JTAG header. This is the JTAG header on this board right here, the Router Station Pro. It's kind of hard to see, but at least it gives you an idea. That's a 14-pin JTAG header. And then here's a Netgear ProSafe firewall, blah, 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 blah. It's got a JTAG header. That's pretty cool. I could think of some things we might be able to do with that. Maybe load our own OS. All right, so how many people have heard of IDA Pro? Excellent. So IDA Pro is pretty cool. It's a nice tool. It allows you to pull up a binary, and then it just walks through, all the assembly and goes, oh, okay, here's this, here's this, here's this. There's also a proximity view that I don't know if they've just included it, but that was what actually helped me very quickly debug what was going on in the code that I was looking at. All right, so in these embedded systems, where did security go? There's no sudoers, right? How many people here use sudo? I think everybody should raise their hand, I hope. If you don't, that means you're running as root, which is bad. There's no shadow. What's the shadow file do? Encrypted passwords, or hashed passwords, right? Absolutely. Why do I care about that? Because only root can see it, absolutely, yes. Because you don't want typical users that are coming onto your system to be able to see that password or that hash. Apparently I've been donated a bug. Excellent. A frog, a dollar bill frog. All right. So again, one user to rule them all. A lot of these systems will have SNMP, Telnet, SSH, and other services enabled. Some of that is appropriate because it's required for functionality, but some of it, why do I need to run SNMP on a device that's going to be sitting on a customer's network, right? So the other thing is using the device to restrict network access, but not to the network. So it's kind of janky, because if the device gets compromised, now you can disable the controls on the device and get access to other components of the network that are part of the management network. Does that make sense? And again, I'm harping on BusyBox. It's a good thing for what it does, but I think we need to probably potentially improve this. So in this particular box, it's essentially supposed to go on a client's network. It had SNMP, SSH, Telnet, oh, and a web service. Oh, that's cool. So SNMP, SNMP was available, had a public string, default public string, like, oh, hey, look, I can see all its IP addresses, I can see the kernel firmware version, all sorts of little useful things, so that now I know what to target when I actually want to go back and hack it. SSH was enabled, makes sense. However, later on, I found out that it's only the root user that's enabled, and they're using a password. Not exactly cool. On some of the versions, you can actually enable Telnet. I think Telnet should just go away. Why take the space on disk? It should just go away. And then a web server. So the web server is where the user goes and enters in stuff, right? Enters in data. They have to be able to set this device up. They have to be able to configure it. Or an installer, a tech, has to be able to configure it. Makes sense, right? All right, so what could I do to pwn? Does anybody recognize this picture? This was the. No, this is a guy at TorCon. Was it 2 years ago for the Tamper Evident contest? Their box went drinking with them. So, if we could only add an account to this device, right? Well, so let's figure out how we can do that. You know, the other thing is we can list the gateway's IPs. So via SNMP, I can figure out what networks were behind it and figure out, oh, there's a management network that sits behind this as well as the IP that I'm assigned and the IP that this device is assigned. So there's multiple networks that I get a privy into because of the SNMP. Maybe I could use that to take and potentially compromise other machines. I did find that other machines were listening on those IPs and that I could get to their SSH port. I mean, that's not cool, right? If this is supposed to be a device that's on the customer's network. I could crash the thing, right? Maybe. Potential. Ideally, I'd want to get a root shell, right? Root shell would allow me to get into the device, compromise the device, see what access it has, and then go from there as a leapfrog point. All right, so some options for root shells. There's a couple different ways we can go about this. Option 1, I can has passwords, please, right? Passwords hashes. Option 2, strl copy, str copy. Does anybody know what str copy is? If you've done C programming, str copy is string copy. A couple years ago, well, oh boy, maybe even more than a couple years ago, there was basically a project going on in OpenBSD to go through and replace any sort of str copies with strl copies so that you have a length bound check when you actually go to copy a string. Because what happens if you don't have a length bound check and you can overwrite that string? Buffer overflow, that's right. All right, so option 1, dump the firmware, either via JTAG or if you have the bin image, right? Find the partitions, binwalk, hexedit, hexdump, any of those. Binwalk's kind of nice because it goes through and finds the headers. It doesn't always work for everything, but that works pretty well. Once you found where the headers are in the code, you then bring it to DD and basically rip the pieces out. Once you've ripped the pieces out, you mount the file systems, you grab the password hashes, crack the passwords via John the Ripper, right? Plausible attack, right? Totally plausible. All right, so str copy. Statagram here? No, too bad. All right, so dump the firmware again, right? Get the firmware either via JTAG or via the binary image. Ideally, well, I'll go into that later. But anyway, then you find the mounted partitions, find the web interface binaries, right? Because this thing has a web server on it. Reverse engineer and identify string copy and memory allocations, right? Once you've got those, essentially what I did is I went and grabbed Metasploit, not because I'm a Metasploit script kiddie, but because it had a Ruby script that somebody had already created to push data onto a stack. So I grabbed it, grabbed an ARM binary, in this case, and then used that ARM binary. And then I pushed C++ data, or compiled data onto that app. Does that make sense? Is this a plausible attack? Okay. All right. We'll do a quick demo of stuff. So here's what happens when you run binwalk. I don't know if you can see this, but essentially we've got, there's a couple of different tools here. Firmware mod kit allows you to take an OpenWRT firmware, pull it down, modify the kernel that's in it, repack it, and then push it back up to the device. Sometimes you could brick a router doing this. Sometimes you can't. But basically what it's using is binwalk. We'll see if this actually gets anything, but essentially, yeah, there you go. So you can see LZMA, so that's a squash file system. So you could take DD, tell DD count, start at this point, skip to whatever, decimal 324, count for whatever hex 144 is, convert that to decimal, or just paste it into DD, and essentially it'll rip that portion of the image out. Because what they're doing is they're packing all these images, all these file systems on top of each other. Then it looks like we have, later on, we have a bzip2 file system or some sort of file system that lives on top of that. That might be, a ext3, it might be a jffs, something along those lines. So you pull those out, piecemeal those out, and then you mount them using a loop file system. Those are kind of cool. Yeah, pretty easy to do, pretty easy stuff. So this is OpenOCD, which is connected to this little fly swatter device is what it's called, fly swatter 2. It's a JTAG device, or JTAG interrogator device. I've already got it pre-configured. It comes up, basically, I don't have the power on the system here. Let me plug that in. There's your problem. All right, let's restart this. And there we go. So now you got all these fun commands, right, that you can run on the system. Most of them require that you halt the system, which is fine. But let's see, are you up yet? Oh, there it goes. So basically what I did there is when you first plug the device in and you've got the JTAG unit on it, it doesn't boot. So you have to go tell it, send the command to reset the system. It now resets the system, and now the system is booting. And this is, Router Station Pro with OpenWRT. It's pretty simple. All right, so it's booted. Now what I have to do in order to dump memory or look at the registers is halt the system. Why would that be? Because you got to freeze them in place. Otherwise they're going to change, right? So issue the halt command. Takes a moment, and it's going to basically halt the CPU for, I think it's 5 seconds. Now we can dump the registers, right? Dump the registers. There's also a thing called dump image that allow you to basically say, go from this point in memory to this point in memory and dump all the memory to a file system or to a file. After 5 seconds, it actually releases the halt, and in this case, it's rebooting. If you say resume, if I remember correctly, it should actually resume where you're at in the breakpoint. All right. Now, let's go to IDA Pro. This is kind of, let's see, let's open. Has anybody used Medusa before? Yes, no? It's a nice little program. So here it is in all its binary glory, assembly language. But here it is in the preview view that allows you to basically go through and go, oh, so here's the main function, right? Main is where you start out all your C code. And then here's where it links into all the other stuff that's here. You know, this one's kind of large to look at, as you can see, and it goes pretty deep. I think a better one to look at is CC search. It's basically a tool that goes through and looks for credit cards on file systems. It's pretty simple. But go back to this search, or this view. You can see there's the sort of the flow tree for how it works. Start, here's a subroutine, here's an init process, here's a subroutine, another subroutine. If we want, we can look for, oh look, there's a string copy. I wonder if we could use that, right? I think there's malloc further down here. Yep. Some sort of memory allocations happening in there. We go and investigate that further. Okay, what happens if I get to the point where I could overflow the stack on that particular memory allocation? So, yeah. So I mean, it's a cool tool, right? But I'm not here to sell the tool. That's not what I do. I don't sell the tool. All right. That worked pretty well. Does anybody have any questions about that stuff? No?
So yeah, you talked about the flash water device.
Yeah.
What sorts of things have you been able to get into with flash water?
So the question is, what sorts of things can you get into with the fly swatter device? It's pretty much, it's the cables that come with it have an ARM 14 pin, ARM 20 pin. I think there's a TI pin chipset as well. I mean, anything that has JTAG on it, you should be able to wire it up so you can get into it. Now, finding out the frequency and the clock cycles may be a little bit more difficult. The chip that I was working with was an Octeon Kelvium from Kelvium, I think is what they're pronounced. Anyway, that chip was a little bit harder to find documents about because it's basically, you know, they're looking at selling it to everybody who's going to make an embedded system. This was a lot easier. This is out on the internet. This is why I went with this, because I wanted to show off that there are tools out there that do this. It just has to be documented. So, and the Airthos chipsets are very well documented. That's what's in here for a CPU. So, all right. So, I basically grabbed this binary blob. This is, you know, on a router that was going at a client point. Mounted it via loop file system. Grabbed the password out of Etsy password, because there's no shadows, remember, right? And then brought it to John the Ripper, and it looks like in 3 seconds it was able to crack it. So that was kind of a fail. And this password is going to be deployed to all the endpoints, right? That's not a cool thing. So that was a learning point. All right, so string copy. This is a little bit more interesting. I mean, that's like easy to do. So we found the vulnerable code on the web service, right? Or we want to. And then we used Metasploit with the linksys apply cgi.rb, because basically all it's doing is throwing data. I didn't really care. I was like, you know, limited in time that I had to do my testing. I was on site for only a couple of days. I have to get in, do my testing, get out, provide results. And so, grab this. There's actually a Linux MIPS reboot shellcode that's out there on the internet. Grabbed it, compiled it, threw it into the interpreter, or into the Metasploit module that I grabbed, posted. And here you can see, this is basically the binary that I analyzed. I've sanitized it quite a bit, but you can see there's a string copy. You can see there's a memory allocation. I don't know if you can see that back there, but there is a string copying and memory allocation within a certain component of this web application. So, and then this is the response. This is actually a packet capture. So I did a packet capture while I hit the Metasploit module because I really didn't want to write output handlers. I was just like, well, let's just do this, capture the packets, move on. Basically, the last end of that garbage is the reboot MIPS binary being pushed across. And then what pops back? Oh, look, glibc detected. Memory allocation corruption. So basically, I overflowed the stack. Followed by this was a backtrace and a memory map of everything that was on the system. Using that, I could have definitely created a shell payload that would have uploaded the machine and basically compromised this machine because they hadn't done their due diligence in limiting string lengths. Does that make sense? I didn't mention option 3, but this is another one. Just modify the JTAG image, repack it, and flash it with the JTAG reader, right, for the JTAG tool. It's very, 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 very slow to use the JTAG to dump firmware, to load firmware, however. It's a lot faster to go through this process and reverse engineer what's out there and use that to gain access than it is to actually use the JTAG, at least from a time perspective. So to give you an example, when I got on site, I didn't have a JTAG reader with me. I basically said, okay, so here's the threat vectors, right? This is what we could do. I'm a skilled attacker. I have a ton of time. We could potentially dump the JTAG, dump the firmware off the JTAG, or via the JTAG. So we brought it to an engineer and said, all right, dump this for us. And 24 hours later, he's like, yeah, it's not quite done. All right, come back another couple hours later. It's done, but it's kind of corrupt. So from that perspective, it was very painful. So I said, all right, give me the raw binary. We'll go through and analyze the raw binary, pretending like we've had several weeks to actually dump the firmware on this. And that's how I got to all these other components of these other areas that, essentially being able to recover the hash, being able to identify entry points in their web service. Is this fun to anybody else? This is fun to me. I may not seem like it, but it's like, whoa, exciting. All right, so what can we do better? Disable the services, right? If you don't need SNMP, you shouldn't run it. If you don't need Telnet, you shouldn't run it. Put in access control lists. I think that's the number one, like super easy. Cut it off. Implement a sudoers with separate accounts. Privilege separation, right? So you can say, oh, here's our maintenance account. It has access to this function. Oh, here's our user gonna check to see if the user is actually stupid or if the modem is right? So you maybe have a tech account and its restrictions. You have all these other different accounts that have privilege separation and logging and auditing. I mean, you do this in the large server environment. Why can't we do it here? I mean, it doesn't have to be complex. You enable syslog and you don't log anything locally. Also a shadow file. I think, if you're going to add separate users, you definitely have to have a shadow file so that you can't recover the passwords from those other users. Or better yet, don't use passwords, use SSH keys. I think this is probably the better idea, in my opinion. You have a public key that you just put on all those boxes, or maybe you generate key pairs for all the different boxes that are out there and you load those public keys. I don't really care, just don't use a password, because now once I get access to that box, I get access to the password, which means I can go to the other devices on the same network and manage them and compromise them. So what can we do better? Code review, right? Knows your IP. Code reviews, I mean, 10 minutes, all right. I'll be done shortly. You can all go to lunch. Code review. So essentially, I mean, this instance where we had code review done on this service, they knew about what I had exploited. So, I mean, it's good that they did code review, but it's also another integral part is fixing those bugs before they go into production. Also, don't put debug symbols in your C++ code for production, because that made it so much easier for me to follow things. Also, assume that the system is owned. Assume that whatever you've deployed out to the user's network is compromised. So if I can recover what's on there, that means that anybody else can. Well, within reason. But it means that you have to assume the device is owned. If you go under that model, your security controls are going to be a lot stronger than if you assume you manage and own the device. Even though you do manage and own the device, but you don't want it to be compromised, or your network infrastructure or other devices to be compromised if one system fails. So I think really if they had done a security review of the firmware, well, basically the embedded Linux distro that they were using, they might have gone, well, maybe we should use a different Linux distribution. Maybe we should use something that doesn't use BusyBox out of the box. Maybe we should put an actual distribution on here with some real security controls in place. Don't use shared passwords for clients, right? Each password should either be individually generated for all those devices that are going out there, or it should not have a password, and it should use essentially SSH keys to log into the device. Period. Done. Again, hardware that's in the hands of the users is out of your control, as far as I'm concerned. Unless you're really paranoid and you have a CPU dedicated for security. And you've got all sorts of other controls. Make things with security in mind. I think a lot of times it still happens. People develop stuff until the point where it's ready to go to production, and then they go, oh yeah, we should check the security on this. I don't know that this is ever going to stop, but it's gotten better, but I still see it all the time. The security should be in the front-end development component. Hey, okay, we've got a value that we're taking in, on our C++ program. How are we going to limit that string length? Are we going to limit that string length? Is the developer going to go, oh yeah, we should do strl copy instead of str copy? And I guess the last statement, ditch BusyBox. Might as well just run real OSs on these things, because they're fast enough and they have the disk space and power to be able to do that. There's no necessity for being able to, or not being able to run full OSs on these anymore. All right, I'm ahead of time, I think. So here's links to all the stuff that I talked about and that I found very useful. The exploits DB is where the ARM overflow code is. Firmware mod kit, that's the one that allows you to download an OpenWRT firmware image, unpack it into directories, and then repack it later on. And then the reverse engineering is a blog post that talks about reverse engineering a Linksys router, similar concept. And I'm probably going to put up a blog post in the next couple of weeks on this, so that hopefully we'll have a little bit more info on there as well, as far as what I can release. The hard part is when you're putting together a presentation, you've got all these screenshots, and you're like, yeah, there's way too much data in that. I can't show that. So we'll put it beyond other people. So I feel like I should flip the slide for these people that are trying to take a picture. All right, cool. Does anybody have any questions?
So you were saying they include debug symbols in there, so they actually had snaps information in there?
Yes. Yes, well, debug symbols that basically allow IDA Pro to have a better outlook on what the code is doing, right? So it made it easier for me to go through and go, all right, there's where I see this, this is where I see this. So.
You mentioned this thing called Medusa. How does that compare to IDA Pro? I'm trying to find something about it online.
So Medusa was just a code that I was running. Medusa is actually a password guessing tool.
Oh, okay. That's what I thought it was.
Yeah.
I thought it was the disassembler.
No. The disassembler is IDA Pro. I'm sure there's other disassemblers out there.
Yeah.
This.
So I eavesdrop a little on your slides while your command line when you were cruising around inside of Ubuntu, and I saw a bunch of MIPS stuff. And for some of the webcam research I did, I was trying to unroll MIPS firmwares. And
Okay.
I had a lot of ridiculous uphill battles trying to do unrolling of MIPS firmware and then mounting and running of MIPS images. I couldn't get anywhere. So was that device a MIPS device? And if so, were you able to actually run anything, or was your approach entirely pulling down firmware or connecting IDA to it through JTAG to hit it that way?
No, my approach. So my approach was entirely grabbing the firmware, the binary, right, binary image, mounting that up, and then reverse engineering it, right. The JTAG was, if I had enough time, this is where I would go, right. Again, it's a time trade-off.
Yeah.
You may have the time to let it dump firmware and try that if you've got access to one of the devices, right? If you don't have access to one of the devices, probably reverse engineering the firmware that gets loaded on that is going to be the easiest. As far as the MIPS stuff goes, some of them do weird encodings with the file systems. Like they'll flip some of the file headers to, instead of being, what is it, LZMA, it'll be LZSQ or something like that in the header, and you may not see that, or the tools won't see that unless you add it to the index finding. So like binwalk won't see that it's got a different header on it because it's a different header, but it's there if you're trying to like actually rip stuff off of firmware or out of firmware, the binary image. CJ?
What do you do with unlabeled JTAG?
What would you do with an unlabeled JTAG? I mean, like if it was a port on a board that was unlabeled,
You got a bunch of pinholes.
bunch of pinholes.
You know it's JTAG.
If you know it's JTAG, I would probably check what the chip is and go look the chip manufacturer up, and then trace the pins back. That would probably be the easiest thing because it's all documented that they've got JTAG. There's only like 4 lines that you actually need to use. It's TDI, TDO, reset, and something else.
That's the zero
Clock.
Day, that's the 0-day countermeasure they're doing now. They're unlabeling the JTAGs and shuffling them a little bit.
Oh, that's funny. So CJ says they're unlabeling the JTAGs and shuffling them a little bit. I don't think that would matter. I mean, you can solder on points onto those. I mean, I remember, I can neither confirm nor deny, but I may have modded an Xbox, put a chip on it, and I remember using like 24, 26 gauge wire to go on the little tap points on the board to solder that on to get a jumper onto the mod chip. So if I can do that with a soldering iron, why couldn't I do that with a JTAG header? Just basically solder little tap points on. I'm sure there's a way to figure out what they are as well. If you can't look at the documentation on the CPU or the chip. Voltage, yeah, exactly. Voltage or an oscilloscope or something like that, because one of them is going to be producing pulses because it's got a clock.
$100 Sealy logic analyzer.
$100 what analyzer?
Yeah, Sealy or analogic.
Okay, Sealy or analogic logic analyzer. Yeah, totally. It's a USB logic analyzer, right? Yeah. You had a question?
Yeah, I was curious. When you found the bug in the CGI, were you had you pulled out the CGI binary itself and were analyzing that, or were you doing that all within the context of the entire firmware?
So there was 2 things. One, I had access to the web interface, so I knew that there was a bug. Like, I would post data to the thing, and it would just stop responding. I'm like, okay, there's something not right here. Once I figured that out, I'm like, all right, I need access to this image. So I pulled the image down and started rooting through the firmware, and went, oh, look, here's the web directory, here's the C++ code. All right, let's grab that and throw it into IDA Pro. Once I threw it into IDA Pro and I saw, oh, okay, here's these values that I'm posting that I know are doing something, but I don't have any output. I mean, it's just silently dying, right? The binary is silently dying. Once I did that and figured out that, okay, this is a, ARM, I can grab some ARM code, throw the shell code on the back of it, and then post it. Oh, look, debug symbols. Now I know what I've done. So now I know there's an overflow here. All right, any other questions? Cool. I think, what do we have for time here? 4 minutes to noon. All right, perfect. Cool. Well, thank you all for coming. If you have any questions, please feel free to let me know. Also stick around for a little bit. Maybe we can play with the JTAG stuff or whatever. So, thank you.